So in this part of the lesson, we're going to be giving some examples of how to apply the fork join pool in practice. And I'll be using the big fraction example to motivate this. And I'll show you several different fork join pool programming models, maybe models, too strong of a word, several different approaches to use fork join pool, all of which, of course, are shown here at the example available at the GitHub account. So the big picture view is that the program, like we've seen before, is going to take a bunch of randomly generated big fractions, and then it'll use a couple different programming models and demonstrate different techniques using the fork join pool alternatives to do operations like reduce and multiply those big fractions. As we will see, these models have various pros and cons. And if you take a careful look here inside the red box, you'll see some interesting results. So there are 4 different approaches in these examples. We're going to look at 3 of them. And a couple things I want you to note. First of all, you'll see that they run, and they take different amounts of time to run. So you'll see test, apply, all, split index is the fastest in terms of run time. And just as an alternative, test, apply, all, iter is the slowest in terms of run time. But then even more interestingly, if you look inside at some statistics that you can get from the fork join pool, it'll tell you, for example, how many steals were used in order to do the computations. And you can see here that apply all iter, which is the slowest one, steals 31 times. In contrast, apply all split index, which is the fastest, only steals 16 times. And we'll talk about this, and you'll see that there were 30 elements in the array that we're processing, and that's where we get this stuff from. Thank you very much. Appreciate that. So we'll talk more about this, but the thing I want you to remember right now is that apply all iter does a lot more stealing than apply all split index and apply all split. Both of those do much less stealing, and when we see the code, you'll see why. In addition to stealing, some of the approaches end up doing more data copying, some make more method calls, and so on and so forth, but others are easier to program. So as usual, there's sort of these trade-offs between simplicity and performance. We'll talk about that. Here's the main program. So what we have here is we've got a main program that will make a stream of big fractions, and we'll make up to 30 of them, because S max fractions is set to 30 for this case. So we make 30 random fractions. These are rather large. We collect them into a list, so we have a list of fractions. Then we go ahead and basically create an operation. This is a function that's going to reduce the big fraction and then multiply it by some big constant. And as you'll see, that this function, even though it doesn't look like it's got a whole lot of code in it, it takes a surprisingly long time to run. And that's because the big fractions are really big. So they take quite a while to do their processing. Which is why, of course, parallelism is a win, right? And then we go ahead and call some of the fork join tests. And I'm going to show you 3 of them. OK, here are the methods we're calling. Each of these are test methods. Test, apply, all, iter. Test, apply, all, split. Test, apply, all, split, index. Each of these call these helper methods that are using the fork join framework in different ways. And you'll notice how each of these method calls uses a new fork join pool. So they each get their own fork join pool to do the work rather than using the common fork join pool. Does anybody know why, for the purpose of testing, I make each of these calls have their own fork join pool? What's the motivation for doing that? Peyton? Exactly. So if once you call the fork join pool, the common fork join pool once, it'll typically create a bunch of threads, and they'll stick around, because that's kind of what they do. And then the next time you call the next one, of course, that guy is going to start with all the threads warm and up and running and stuff like that. So it'll give you a skewed result, because whoever gets called first is going to perform worse than whoever gets called second, even though there may actually be fundamental differences in the way the different approaches work. So we're trying to basically start each fork join pool cold, so they're more likely to be apples-to-apples comparisons that are meaningful. All right, so let's take a look at the apply all iter method first. This is the simplest way of doing things. And so apply all iter, as you can see, takes a list, a function, and a fork join pool. Those are the 3 things it gets passed. And what it does is it's going to apply the function op, for operation, to all items in the list by calling the various fork join methods iteratively. That's the key thing, iteratively. And we'll talk about what that does and why that affects various properties. So here's what happens. We say new fork join pool passed as a parameter. That should actually be fj pool. Sorry, I'll have to go back and fix that. Invoke new recursive task. So we're going to make ourselves an anonymous inner class instance of a recursive task, and we're going to invoke it in the fork join pool that's passed in here. And this code is sadly more verbose than we would like, and that's because fork join pool came from Java 7 before they had lambdas and functional interfaces. Therefore, there is no functional interface. There's a class, so you can't do all the cool little lambda or method reference tricks to get rid of some of the additional bloat. So you just have to suck it up and give yourself ever so much carpal tunnel syndrome to write that code. Here's the compute method. So this is this method here. This is just expanding what that method does. As you can see, this is a very canonicalized way of doing things. It's going to implement the main fork join task that's going to do all the parallel computations. We create a list that will hold the fork join tasks that we're forking. We'll see where they get forked in a second. So this is going to be the things that are forked that we're going to eventually need to join with. And then we also have a results list, a list of results, and that's going to be used to hold the results as things complete. So we make these two lists. They're just linked lists, nothing tricky or fancy here. This loop is the one that does the main processing to get things up and running. You can see it iterates through every element in the list. And for each element in the list, it will make a new recursive task that has a compute method. I'll talk about what the compute method does in a second. And it's going to then go ahead and fork that task. So remember what fork does? Fork arranges to run the tasks somewhere in a pool. And fork returns this. It returns the item that was forked. And so we simply turn around and just add that to our forks list. So we're basically going to use this forks list to keep track of the task we just forked. All right, so we fork all those things off. Now notice here that whenever a given task runs, because of course it's just being arranged to run, but whenever the task actually is run by a thread in the worker thread pool, the compute method will get called back, and that will say op, which is what's passed in here, dot apply, because it's a function, to t, which is the current element in the list. So this is going to basically run in its own worker thread eventually, and it'll apply the operation, and it'll return the result of whatever that operation was. And of course, we'll get the result back by this next loop. But before I go to that, any questions about what's going on here? Andrew? Recursive task? Great question. The question is why is this a fork join task, not a recursive task? Because of course this is a recursive task, right? Well, the reason is because I was just trying to fit things on the slide. And so if I'd put recursive task here, then I couldn't have done my clever little trick here of calling fork and then directly adding it in to this thing. I'd have to say recursive task, t, or recursive task rt or something equal new recursive task. Then I would have had to have said fork rt, and then I would have said forks.add rt. And so it would have been more verbose. So if you program to the base class, which is fork join task, because recursive task is a fork join task, it extends fork join task, then you can do this clever trick where you fork and you add, and it all ends up being done in a very nice, concise way. So that's why I did it. If I was actually writing production code, I might have stuck with using recursive task instead of fork join task, because it might have been a little bit more clear what was going on. But I was making my slides get too big, and I couldn't fit them all on one slide. I also kind of like this idiom. It's kind of cool, because once you get used to it, you're making a task, forking it, and adding it to a list all in one fell swoop. So it's really very concise, maybe too concise. That's a great question. Any other questions about forking? So this implementation, this is really important to understand. In one thread of control, we're going to fork every other thread. Sorry, every other task, not every other thread. So this one thread will fork all the other threads. So I'll show you a visualization of this in a second. But what happens here is the deck of that one worker thread now has all the fork join tasks in it. And in order for this thing to work, then all the other threads in the pool have to come along here and steal the work from that one worker thread's deck. And as it's going to turn out, that's going to incur a fair amount of overhead to do that, as you might expect, because they've all got to come and steal. So keep that in mind when we talk about the other ways of doing things. So this way, as you can see, is really simple to program, but you end up with more contention, and it takes longer to get it up and running. Once we've forked everything off, then we simply go here and we join the results and add them to the results list. So down here, we iterate through every task in our forks list, and we say task.join, and we take the result of that, which will be the result of computing this thing, and we add that to the results list. Now, these guys may not compute, they may not complete in the same order that they were forked. That's perfectly fine, right? We don't really care. We just want to get the results back. We don't need to have them obey some particular order. A couple things to note here. Remember that the join here, because it's a task join, this is the pitch-in model, right? So in this model, if this guy doesn't join right away, this thread can actually join in and run other tasks in order to get them, or you can run the other tasks in order to get them done so it can get everybody else finished earlier. So that's the pitch-in model. That's the way the fork join tasks work. So that's one of the distinctions between a Java thread join, which really puts the thread to sleep, and a fork join task join, where the thread that's calling join can pitch in and do other processing. And then we return the results. So that's what this implementation looks like. This implementation, I think, once you get your head around the basic ideas, is actually pretty simple to program and understand, because it's iterative. Fork all the tasks, join all the tasks, we're done. Let's visualize what things look like. So I'm just going to show little snippets of the code, and I'll show you what's going on under the hood. So when I say fork join pool, which again should be FJ pool, invoke, that adds this task to something called the shared queue. So the shared queue is this queue that non-fork join task clients use to get work into the fork join pool. Right, so this is an external client. That's the name for it. It's an external entity, not a fork join task. It's an external entity, and that goes ahead and puts it in the shared queue. And that also then wakes up threads in the fork join pool. And here's what happens then. So one thread will wake up in the fork join pool, one worker thread, WT, say WT1. And WT1 will go ahead and run this loop, because it'll process this task, the one that was put in at the beginning. So it'll pull it off the shared queue, and it'll process it. And notice how it sticks every item into the fork join threads, into the worker threads work queue. Puts them all in there. So they're all in one deck. And then the other threads in the pool, to get work to do, because they're eager beavers, they want to get the work done, they're going to come and steal this guy's tasks and start to work on them. And this guy has done all the work, so there's no further subdivision of tasks. So these guys are just going to steal the tasks, and then they will go ahead and run. So it turns out that work stealing is fairly high here, because as you saw from the original statistics, we're stealing a lot of things. There's really one steal for every piece of work. But copying and method calls are low. There's not a lot of work to put it all back together again. It's work to get it partitioned out to do the processing, but once it's done processing, there's not a lot of other work to get it all back together again. So kind of merging is simple, but forking is more complicated because we have to steal. Any questions about that? And then when we join, it just pulls all the pieces back together. And the worker threads pitch in to help compute the subtasks. So this, like always, is the Jiffy Lube model of processing by pitching in. Of course, Jiffy Lube doesn't really work that way, but the idea there was that with Jiffy Lube, if you take your car, actually I thought about this some more. So you go to Jiffy Lube and you've got multiple car bays in your Jiffy Lube, maybe 3 of them, and each bay has a pool of workers working on them. And so what you could do if you wanted to pitch in, you could help, help change the oil or check the gauge or check the filters or top off the washer fluid or fill the tire pressure or whatnot on your car. But you could also go and help with the other cars too, right? So that's kind of like, working with things in other threads. You can go and do other work that aren't really from your responsibility. And that's what the cooperative model is with the fork join pool. All right, let's take a look at a different example. This one is called ApplyAllSplitter. And this approach is going to use recursive decomposition in order to do the original partitioning of the problem up into pieces. And if you recall, when I showed you the statistics, which I'll regurgitate later at the end when we do the wrap-up, there was much less work stealing going on here. And you'll literally see why there's much less work stealing here in just a minute. All right, so what we do here is we make ourselves something called a splitter task, which extends recursive tasks. Arturo. It means it runs faster, because the more work stealing there is, all things being equal, which they're not always, but if other things are equal, if you have to rely on work stealing, you may have some problems. What would be a problem with work stealing? Maybe to make that point a little bit more clear, let's go back and look at the picture. So this is the original picture. Matt. Right, so two problems with work stealing. One of them relates to saturation, as you mentioned. So one problem is, remember how we steal things in the first place? You always steal from the end of somebody's deck. And if, let's say for sake of argument, we have 8 threads in our worker thread pool. If this guy has a lot of work in his deck, if WT1 has lots of work in his deck, then to steal the items, all the threads are going to have to come to his deck and get stuff off of the end of his deck, right? Using the FIFO model of working, get the item at the end. Well, they're all going to have to contend for that lock, right? So problem number one is they're all going to have to come contend for the lock. So the contention for the lock will be high. And the second thing is that all these other threads have to realize they have to go over here and they have to find this guy and have to pull the stuff off. And so it just takes a while to do that. There's mechanisms that the fork join pool implementation uses that involves, having threads scan across all the different queues in sort of an arbitrary random order, trying to find one with work. So that's just going to take a while to get up and running. In contrast, when we do the recursive decomposition, as we'll see here in a second, you'll see that, first of all, you're not going out to the same queues, so there's much, much less contention. And number two, just the way it's breaking itself up, you have a nice balanced tree, so you don't have to keep searching all over the place trying to find work to do. You just end up with work to do for the most part. And then that's why the work stealing is lower, and that's why the performance is often better. But there are some trade-offs, as we'll see here in a second. Okay, so ApplyAllSplitter. We make ourselves a splitter task. That's going to partition the list recursively and then run each half in a fork join task. And then the main entry point here is we're just going to go ahead and say fork join pool. This should be FJ pool. Invoke new splitter task. And it starts by giving it the entire list. So we start out with the whole list as the beginning. Now, you'll see in a second it's going to get partitioned into sublists. Here's what splitter task looks like. It has a field called mlist. And this is basically a sublist. This is the list that this particular task is working on. You'll see how that works in a second. And the constructor just assigns it. So whatever it is given here, it just goes ahead and assigns a reference to that. All right, here's what compute looks like. Compute looks quite a bit different from what we saw before. So what compute does is it's going to recursively perform the computations in parallel. So we come in here and we say, is the size of our sublist less than or equal to 1? So, if it's a big list, the answer is no most of the time. But you'll eventually get to a point where you've got one item in the list. And in that case, we make a new result list. And then we go ahead and we iterate through the list that we've got. And for each element in that list, which will just be 1 in this case, typically, we apply the operation on the value t, which we get from here. And then we store that result into our result list. And then when we're done, we return that sublist. So we have a results sublist that gets returned. And it'll typically have one item in it. Now, where that's coming from, of course, is by the time you get to this piece of code, we've split the list, split, until we have an element of size 1. If we have n items in the list, how many times can we split it in half to get to size 1? Log n, right. So it's going to be a nice balanced tree of splits. So let's take a look at the code that does the splitting. Well, this looks like a lot of code. It's actually just kind of jammed together to fit on one slide. It's not quite as onerous as it looks at first glance. But it is more complicated than what we saw before, right? The iterative version we saw before was a lot more leisurely if you look at it. It's much more clear what was going on. So what we're doing here is we figure out the midpoint of the list. We divide the size by 2. We then go ahead and we make a new splitter task. This is the left task. And that's going to handle a sublist from 0 up to the midpoint. So we're going to copy the list from 0 to the midpoint, make a new splitter task, fork that new splitter task, and then assign it to this fork join task LT. So this guy now has been arranged to run in another thread of control. And what it's doing, by the way, is, as you'll see in a second, is it's recursively doing this stuff. So it's splitting and it's handing off half the work to one thread, and then it's going to keep the other half of the work for the calling thread. So what it does is it basically splits the current list into a sublist. So now it's half as big from the midpoint to the end, right? So now we've got 2 lists that are half as big. And then it calls compute. So this call is not actually taking place in a different thread. It's just staying in the same thread it was already in. And that's just to avoid having to make unnecessary threads. So this guy will then run in parallel with that guy, right? So the fork guy is off running. We're running ourselves here. And then after we're done with our computation, we then just say, hey, join me up with the left-hand side when it finishes. And of course, that pitches in, like usual, to do other processing. And what we get back then is the left result. And then we say, add the right result to the end of the left result and return the left result. So this is just classic, sort of divide and conquer, right? And this is divide and conquer. You look up divide and conquer in the dictionary, there should be this code, right? This is divide and conquer. So you're dividing it in half. One half runs in one, or you give one half to one task, which may further decompose it, by the way. You give the other half to this guy, and he may further decompose it, by the way, right? So we've divided and conquered. They both go off and do their thing, and then at some point, compute returns, join returns. We add the results together, and we've got a sub-result that's the result of 2 sub-results, and then that gets passed back, and it gets joined by something above. So even though, as you'll see, this solution is faster, it ought to be faster because it's more of a pain in the butt to do, but it's harder to program, and it's also a little bit harder to understand because it's recursive. I mean, once you get it, it's not too hard, but when you first see it, you're like, wow, what the heck is going on here? So it's a little bit more complicated. So let's visualize and see what this looks like. So here we go ahead and do a new splitter task. So we put our task in the shared queue. And then at that point, these guys are going to be forking and computing. And because of the way it's doing the break things up in half approach, we end up with a more balanced set of elements across the various threads in the worker thread pool. So there's not nearly as much stealing going on. There's a little stealing, but not nearly as much stealing. However, even though there's less stealing, there's more copying, right? Because we have to copy all these sublists all over the place. And there's also more method calls because we're having to do this recursive decomposition with extra recursive calls. So the overhead is somewhat higher, but we're stealing less, right? So, is that a win? It kind of depends on a variety of things. And you can see again that we fork and then we compute, and we don't put compute in its own task. We just stay in the task we were in. And that's just a clever trick to avoid unnecessary context switching. All right, so we have a nice balanced tree of joins, and so that works well. So let's take a look at a third approach, right? So, yes, Joe? They are, so figuring out how to split them in half takes constant time. So the question was, how long does it take to do these splits? Let's go back and look. Okay, so figuring out how big the thing is takes very little time. I mean, it takes almost no time at all. Right? It's like just divide it in half. The part that takes some time is making a copy of the left-hand side and making a copy of the right-hand side. That's the sublist call makes a copy, right? So you're copying the data. Now, and again, in this particular case, it's like an array of integers, so it's not a huge amount of the size is not, you know, oppressive, but it still takes time. It takes time to do that. So copying takes time, and also arguably, this might take some time if you have to reallocate your arrays. So it's a non-zero amount of time. Yes, Peyton. Yeah. Great question. Bruce had asked an interesting question about this, which I looked into and haven't got a definitive answer, but I'll see if I can take a shot at it. So remember how this is working under the hood. The fork join pool, by default, is going to try to keep the number of worker threads approximate to whatever you requested it to be, or whatever it decides is the right value. So there's two different ways. When you make a fork join pool, you either give it a size, like 8, or it figures a size out. If it figures a size out, it takes typically the number of cores on the machine, and if it's a common pool, it minuses 1, but it's typically the number of cores. Now, you can make a larger number if you explicitly give a constructor. Let's say, for sake of argument, just to make the discussion interesting, that the number of worker threads in the pool is the same as the number of cores, so 8 as an example. So the fork join pool is going to try to keep 8 worker threads there, you know, as much as it possibly can. Now, remember we talked about managed blockers? So managed blockers would apply, not for this example. This example is a totally compute-bound example, right? It's just doing computation. There's no I/O involved. But if we were doing I/O and we had a managed blocker, and you made an invocation for a fork join pool operation with a managed blocker, then it would go ahead and temporarily compensate and add additional threads to the pool. So it can grow the number of threads in the pool if needed. But then once things aren't used for a while, it shrinks them back down again. So it tries to keep it. So for a compute-bound application like this one, you have 8 cores, and you're going to have 8 cores. For the one where you use the managed blocker with I/O-bound stuff, it might grow, get bigger, and then would shrink down later. Now, Bruce had asked the question about what happened on a big little processor that can change the number of cores dynamically. And I think the answer at the moment is they don't really handle that case in the implementation of fork join pool. If that was something important, then they could simply keep track of that by some kind of callback scheme, which could be notified when the number of cores changed from big to little, or more big or more little, or whatever it was. And then they would simply use that as the new set point for the feedback loop, the control loop that tried to shrink or grow the number of threads in the pool. Because keep in mind that the fork join pool already knows how to expand and contract the number of worker threads. So it would just have to have some external way of knowing that that had changed, and then it would take that into account as it ran. So it might not change, instantaneously, but the next time it had to make a decision about whether to make a new thread or not, it would say, oh, gosh, I see the number of cores is now half as what it was before. I better not make that new thread, unless you use the managed blocker, of course. Okay, so let's take a look at an example here. So this is a good example. So what's going to happen when we call fork here? This guy is going to get stuck into a. He will be put at the head of the current worker thread's deck, right? So fork always puts it there, and then this guy will then go off and do compute in that thread. So because he's going to call compute pretty much right after calling fork, he's not going to get around to whatever this thing is here right away. So chances are that this guy is going to be stolen, whatever the fork was, is going to be stolen by another thread. But what's going to happen is that then, because we've done this in the recursive decomposition way, then that other thread will then do the same thing, and it will create stuff, and that'll let another thread steal from it. So it'll vary, each thread will put something on its deck that it won't get to right away because it's going to do computes after it does a fork. Someone else will steal it, but the stealing will take place very rapidly because there's not a single thread that put every single fork join task on its deck. Instead, they're going to recursively put them on their deck, and then another thread will steal, and then they'll steal. So basically, it's like a tree of stealing as opposed to a linked list of stealing, if that makes sense. And that's why the work stealing count is so much lower for the recursive decomposition approaches, even though there is some stealing. And also, just to make another point real clear, you're not always stealing from the same deck. You're stealing from different decks in different threads. So you won't have the same, thundering herd problem of everybody converging on that one deck trying to get worker tasks from it. Yeah.
What if, like,
Yes. Oh, then what'll happen in that case, if you only have a small number of threads, then the queues will simply get larger. And so they'll just, actually, it probably won't make that much of a difference because queues getting larger really aren't a problem. The key issue here is keep the cores working, right? Yes, exactly. So it's keeping the things distributed, but it's keeping the cores busy. So if you only have so many cores, as the key is to keep them all busy all the time and to do that with as least overhead as possible. So that's the win. If you don't have any more cores, the queues will just build up, but that's the instant that a worker thread has nothing to do, it'll get something off its queue right away. Or the second it finishes whatever it's working on, it'll go back around and find the next item. So it'll go very quickly. Other questions? Okay, so let's now see if we can do sort of the best of all worlds, right? So we'd like to come up with something that is going to be recursively decomposed, because we saw that reduces stealing, but we'd also like to do something that doesn't require so much copying, because that's kind of annoying, right? Having to keep copying stuff. So let's see if we can make it better. So this approach is called ApplyAllIndex, and you'll see why it's called splitter index in just a second. And what it's going to do, as you'll see, is it's going to end up doing recursive decomposition, but instead of subdividing the list, it's just going to push indices on the stack, if you will, and it's just going to work with the indices as opposed to actually having to make a full-blown copy over and over again. Now, it does have to do something extra, which we're going to take a look at, and this is really maybe too clever for its own good, but it's the only way to do it. So what this thing does is it comes in, and the first thing it does before it does anything else is it makes a new array that's going to be used to hold all the results. So we need to make an array that's big enough to hold every operation on each element in the original list. So that means it's going to have as many items as the list had. Well, in a normal language like C++, this would be trivial. In a language like Java, you have to stand on your head and use some kind of wacky reflection-like mechanism. So here's what we have to do. We want to make ourselves an array of t's, right, where t is a generic type passed in as a parameter, as a generic parameter to this method, to this helper method. Well, Java really, really, really doesn't want you to do that. It really doesn't like you making generic arrays using generic things. So we have to do some really sleazy tricks. We have to say array.newInstance. So this is a factory method on the array class. And we're going to go ahead and we're going to figure out what the type of an element of the list is. And so we darn well better have at least one element in this list, otherwise this code's going to blow up. I probably should make a check here to look for that and bail out. So we get the type of this, and we make a new array of that type with this many elements in it, and we cast it to be an array to t. So now we've got this results array that's an array of type t. And you would be surprised at how complicated you have to be in Java to make this work. But it's possible. It's really sleazy, but it's possible. So now we've got ourselves an array. We're now going to make ourselves a splitter task that extends recursive action. What's the main difference between recursive action and recursive task? The return type, right? So recursive task has a return type from, join will actually give back a value. Recursive action, you don't have a return type. You just have a join, which just is a synchronized point, which we'll see. All right, so we go ahead and make ourselves an array, which yes, it's ugly, but oh well. You can take a look here for learning more about how to do this. Here's the splitter task that's a recursive action. We make ourselves a new instance, which again should be fjpool. And this says new splitter task 0 list.size. So what that's doing is that's saying, I want the entire range from the beginning to the end. So it's going to kind of push, if you will, 0 to the end as the first item that we're going to work on. And then after this recursive call chain finishes, which we'll look at in a second, the last thing we're going to do is we're going to take the results. Notice this is an array of results. And we're going to convert it back to a list, because that's what's expected to be returned here. There are other ways I could have done this, by the way. I wrote the code like this because I wanted to make everything self-contained. I wanted to have all the methods have the same signature. Another way of doing this, if I didn't want to be quite so sleazy with my using the array new instance factory method, would have been to pass in a results array and just do it in there. That would get rid of a lot of the overhead and complexity here. All right, here's splitter task. So splitter task extends recursive action. And you can see that splitter task, unlike the splitter task we had before, this keeps the indices, not the actual contents of the sublist. So it just keeps the indices, which are indices into this array of results. So we store those things, and here's the compute method. This is all going to be done in parallel. So the first thing we do here is we find the midpoint, and if the midpoint is the same as the low value, then we're at the base of the recursion. And what we do in that case is we go ahead and we get that item out of the list, we get the mloth item out of the list, and we apply it, and then we store the results into the results array at that index. Arturo? No, these things, that's just a right shift by 1. So right shift by 1 is the same as dividing by 2. For various reasons, I think just because it's fun to know this little clever trick. Sometimes people, especially if they don't trust the Java optimizer, can figure out a divide by 2 is the same as a right shift by 1. They will sometimes write code like this. I think older versions of Java probably didn't have optimizers that could figure that out. I would hope newer versions of Java, that would be an optimization they would have automatically, but all that's doing is just saying low plus high divided by 2. If you read Java code, you'll see lots of uses of that. Okay, so we apply the operation, get the item out of the list, apply the operation, store the result in the results array. So that's the the basis case for the recursion. Otherwise, we're going to use recursive decomposition. So what we're going to do is we're going to create a new splitter task, which is going to be low, and we're going to set low to mid. So it's low to mid, fork it, store it here. So we're going to go ahead and start this guy working. And then we're going to call compute. And notice, by the way, in this particular case, we're not having any return values. So compute just computes, right? And the reason we're not having return values is it's storing the results in this local array. And then the last thing we do here is we call join. Now, join is very interesting and very important. So what join is going to do, it's going to say, wait until the left task is finished and then let the flow of control continue. And as we know, it pitches in, blah, 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 all that good stuff. Very, very important that we have join here. And the reason for that is if we don't call this call to join, then it's possible by the time we're all done that the different threads that work on different parts of the results array, because remember each of these threads is working on a different part of the results array, they may not have the memory consistent when we're going to do this very last operation, where we're going to take the results and convert it back into a single list. So it might turn out, if you didn't use join, that different threads would not have the memory consistent by the time this code was called here, which would lead to chaotic results. So this is what's called a synchronization point here. And if you read the Stack Overflow discussion, it talks about memory visibility in fork join. And the key issue here is make sure you call a join in order to make sure that the memory barriers are properly used to flush the cached values out so they're globally visible. It's basically a memory fence that's used to make sure all the memory will be visible. This is confusing, and it's easy to not understand why this works, and the reason you wouldn't understand why it works is you don't understand that join is a synchronization point. This implementation is also a bit hard to program and understand since it's recursive and it's also using this crazy, generic array trick. However, as we'll see, it's also going to be a little faster. So what we're going to do here is we call invoke, and basically the tree of tasks is pretty much the same, except that work stealing and intermediate copying are low. Of course, we had to make a copy. We had to make a new array at the beginning, and we had to make a final copy from the array version back to a list at the end. But all the intermediate copies were avoided. But we still have these extra method calls, right? We have all the method calls for the recursive decomposition. Okay, so those are the three different versions. Let's kind of summarize all these things and compare and contrast them. So there are pros and cons with each of the programming approaches we just saw. The iterative model that we did is very simple, right? You just got two loops. You fork, 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 and then you join, 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 join. And this, of course, relies on work stealing under the hood to make everything work. So it's very simple, but it has more work stealing. So if you take a look here, you can see the ApplyAllItter has a large amount of work stealing, whereas the other approaches have less. We'll ignore this one here. This is just using the invoke all method that comes out of the box by the Java fork join pool. So as a result of this extra stealing, the performance is a bit lower. Now this is not, ridiculously lower, but it's lower. Recursive decomposition, which is what the split versions do, incur fewer steals. And by the way, just if you're curious, if you bump up the number of items in the array, like let's say we have 100 items in the array, you will see that the iterative version will have 100 work steals, and the other recursive decompositions probably have like 16, right? Because they grow at log n as opposed to, or they grow at a different order of magnitude than the iterative one. Not sure, log n may not be quite the right value, but large numbers of items will only require a small number of steals. So it doesn't go up, it goes up much slower for the recursive decomposition versions. And so as a result, performance is often improved. Now, again, this is not, your mileage may vary. There are different scenarios under which this is a win. And a lot of it has to do with other factors like how big is each computation. If you do very, very long running computations, let's say we're going to do, some really complicated mathematical expression for each element in the array, then the overhead of work stealing kind of goes into the noise, right? If you're doing really long computations, the fact that it took a couple hundred, nanoseconds or whatever to steal, who cares? Because it took 10 minutes to run the computation, right? If you're doing very short-lived computations, then obviously the overhead of the work stealing matters more. So that whether it's going to make a difference or not really depends on the length of the computation. And when I was fiddling around with this, I would do things like change the use of multiplication to addition or something, and that made a difference in terms of the runtimes. But this is also more complicated to program, right? So, all things considered, this code is pretty easy to understand. You're just making two loops, whereas this code, while not that complicated, is more work, and you've got to make sure you split things in half properly and so on and so forth. And then it also does this extra work in terms of extra method calls and these other things, right? So there's other stuff that comes along for recursive decomposition. As a general rule of thumb, recursive actions overhead is a little bit lower in this case than recursive tasks overhead. Not by a whole heck of a lot. and depending on how you run the tests, you might get different results. But you could normally think that not having to do those extra copies is probably a win. But recursive action is a bit more idiosyncratic, right? This particular approach where we're going to have the generic arrays, that's just wacky, right? If you look at this code, you probably have to think, pretty hard to figure out what the heck's going on. That's why I said another alternative approach to this would be to just have this method pass in the results array here at the top. And then you could make it much cleaner, right? You wouldn't have to do all this stuff. Okay, so that's the end of the fork join discussion. Any questions about any of that?